Okay, as I said, today we are going to, you know, try to take the polar plots and ultimately from the polar plot, we would like to go to the Nyquist criterion, which will tell us about the stability of the system. So we will start by the polar plots, okay? We will have an idea about the polar plot. How do we sketch the polar plot for, for certain frequencies? We cannot cover the entire spectrum of the frequency, and similar to what we have done in the root locus, we don't, graph all the value of k, let's say, okay? It will be the same thing in here. So the polar, what's the polar plot? Suppose I have a complex function. Suppose I have f of j omega. This is basically is a complex function. Either I will represent it by the Cartesian representation, which is, let's say, a plus j b, or I can put it in terms of magnitude and angle. So the polar plot basically is nothing more than, varying omega, and for each value, I will get the magnitude and the angle. It is equivalent to the Cartesian representation. So basically, what we are saying, if I have a transfer function P of S, I change S to j omega, okay, and then get the graph, get the for each omega, I can get a value, okay, sketch all the value, change omega and sketch all the value. So either you will have, this is the polar or this is the Cartesian representation.
Doctor,
They are related. Yes?
isn't S equal to j omega plus sigma?
Exactly.
Why don't you, what is the sigma?
Which one? This one?
No, where is the sigma when we put j omega?
What do you mean sigma? Basically, you will have, okay, this can be represented as, let's say, a plus jb. This is the real part of the function from here. And this is, b is the imaginary part. If you want to put the what, sigma in here and j omega, this is, okay, that's what you are saying?
Yes.
This is basically, if you take the S-plane, in the S-plane, S equal, we said, sigma plus j omega. So this is, and if you are talking about the S-plane, I have sigma is real x's. Okay, basically, all what we are saying, sigma and omega, they represent the real x's and the imaginary x's. That basically what they are representing. I don't know, is that what you are asking?
Yeah, but I'm not sure why we don't put it like b of j omega plus sigma. Why b of j omega?
I have a complex function. Oh, why don't you put, okay, why don't you get S equal sigma plus j omega? Oh, you are looking, why I don't take sigma?
Yeah.
Okay, this is what we have said before in the, sinusoidal analysis, okay? We take S equal to j omega, we ignore sigma. We don't take sigma. This is because, we are looking for the, steady state analysis. In the steady state, remember the transient will go. This, if you remember, the frequency response. The first lecture in frequency response, we talked about it. In this representation, we will setting S equal to j omega. Okay, I didn't get you at the beginning, but this is basically, yeah, you take sigma to be 0 because we are talking about steady state. Sigma will come, if the system is stable, it will represent the transient part of the system.
Oh, okay. So use sigma for the transient.
Yes. So since we are doing steady state analysis, so usually in the steady state, this is look similar to if you go to the Fourier. How do you relate the Fourier to Laplace transform? What do you do?
It says replace S by j omega.
Exactly. This is what we are doing in here.
Yeah, I see now.
S by j omega. Or if you are talking about the circuit, the phasor analysis, basically we are talking about steady state analysis. So sigma will be ignored. We set S equal to j omega. And I thought this is what we had said from the beginning in the frequency response.
تمام واضح دكتور يعطيك العافية.
Okay. Okay. So basically, if I have, a function, I can represent it either in the polar representation or the Cartesian representation, and they are related. Basically, suppose I have this one, P of j omega, let's say equal to 5 plus j omega. Okay. If omega equal to 1, where do I locate this one in the complex plane? Okay.
You have a magnitude of root 26.
This is imaginary. What?
Yes.
So either,
And this,
so this is going to be 5 plus j1, so 5, and here I'm going to be. Or I will take at omega equal to 1, this is j, so I will have 5 plus j1
yes,
equal to root of
26.
5 square plus 1 angle of tan inverse of omega over 1 over 5. Okay, either way. So either in the polar I can represent, or in the Cartesian.
ليش أخذ يا دكتور شكل why it takes the shape of heart?
Okay, this is okay. No, this is not this one. This is different function, certain function.
جميل.
It's a general function. No, I just want to point. I took only one point. Basically, okay. In the polar representation, you take the real axis to be, okay, this is the 0 reference, this is the angle equal to 0.
Yes. We have taken this in Math 201.
كيف?
We have taken this in Math 201, all shapes in polar in details.
Yes.
In the integration
We are
in polar,
using the polar.
everything we have taken in Math 201.
Okay, we are using the polar. Okay. Now, properties of the polar plot. Okay, the polar plot, P of j omega plus alpha, where alpha is any complex constant, is identical to P of j omega with the origin of the coordinate is shifted by minus alpha. That's basically, if I sketch P of j omega plus alpha around the origin, I'll get certain shape, let's say. It will be easier for me, or I can, at a certain point, this is minus alpha, and my graph, all the graph will be shifted to this shape, in this shape. So I can, what I'm trying to say is, rather than, if you have a function, okay, let's say, okay, where do you think the application here we will use? We will be using this application?
Maybe in radar, Doctor.
This application.
Radar.
Where?
In radar.
No, in here, so far.
You mean the stability and all of that stuff, the stability?
Yes, but look, suppose I have a system, this system. Okay, this is Y and this is R. What will be the characteristic equation of the system?
The characteristic equation 1 plus GS.
Okay, 1 plus G of S, H of S. Or in the frequency domain, so it's going to be F of j omega equal 1 plus G of j omega, H of j omega. So what I want to find the polar plot of this F of j omega. I'll have 1 plus this quantity. What we are trying to say, it would be easier for me to sketch F of j omega minus 1, which is equal to G of j omega, H of j omega. Because this is already given in, simple form and poles and zeros.
Yes.
So rather than plotting this and I'm encircling, let's say, the origin, now in here I will sketch this one, which is easier, but I have to refer to the -1 rather than the origin.
Yes. Because if you keep it with 1 plus 1, you will have exponential 1 plus something.
Yeah,
So it will not be.
no, it will be difficult. It will be okay.
Yes.
It will be much easier to sketch this one alone. So this is where we are going to use this property. The other property, okay, the polar plots of transfer function on a linear time invariant, this is exhibit conjugate symmetry around the real axis. That's basically if I do sketch and my sketch, let's say, come here, then for positive frequency, let's say for negative frequency is going to be the mirror image of it around the real axis. And this is very important. That will, we are going to see, we take the range of frequency from -infinity to infinity. So what I will do, I'll focus on from 0 to infinity, and the other one, I'll just, mirror image of it around the real axis or the horizontal axis. One more thing. The polar plot can be obtained from the body plots. So what we are saying, the polar plots and the body plots, they are related. Okay. For example, suppose I have omega, okay, the magnitude and the phase of G of certain function, let's say G of J omega. I want to sketch, okay, I want vary omega, and let me get the magnitude and the phase. If I want to do a body plot, what do I do?
We determine the corner frequency and.
Suppose, okay, forget about corner frequency, just a sketch. Okay, you have points, omega, this is magnitude, this is angle.
So 20 log the magnitude.
You take 20 log of this one, 20 log of the magnitude.
Of the magnitude, yes.
Versus omega or log omega.
Versus
and
log
then
of omega, yes.
The other one is going to be the phase, okay, versus log omega. In the polar, what do? Rather than having two graphs, you will have one graph where for each point, let's say, in this frequency, correspond to a certain point in here. So it's same information, but different representation. In here, okay, they are versus omega. In this one, I take omega as parameter and parametric, and I will sketch those, this one versus this one. So if I have the body plot, I can, from that one, I can get the polar plot. This is what's the remark. Because ultimately, look, we did the approximation when we talk about corner frequency, that's approximation. But the exact one, you just vary omega and get the magnitude and the angle and the phase and sketch them. Okay? Is this clear?
Yes. على المثال دكتور, with the examples it will be clearer.
If?
With the examples it will be clearer.
It will, inshallah. Let's take the example. Suppose, okay, I have, this is my Oculus system.
Yes.
Okay, find the polar plot, or find the polar, sketch the polar plot. Sketch the polar plot for the system. So basically, first of all, I have to get GH of J omega, which is equal to 1 over J omega plus 1. So what will be the magnitude?
1 over root omega square plus 1.
1 over 1 plus omega square. What about the angle?
Tan inverse minus
Minus tan,
tan
because
inverse. Yes.
omega, because the
Omega, yes.
because look, this is in the angle in denominator. So this is one way of representing the system.
طيب دكتور سؤال.
تفضل.
زاد فضلك. Now we need to know the shape of 1 over root 1 plus omega square, revise the shapes, the common shapes or the common graphs, or we just determine omega for take omega in a table, values for omega, and just sketch it one by one.
No, look, what we are doing, okay, first of all, do you agree this is what we have?
Yeah, of course.
Okay, now let's come and take, we want to graph this one as omega goes from 0 to infinity. We are not going to take all the points. Let's take few points and sketch them. Suppose this is the, okay, G of J omega plane, or G of S plane, they call it. They call G of S plane. Okay, this is the real, this is the imaginary. Now, let's omega equal to 0. So, if omega equal to 0, what would be the magnitude?
It's 1.
So, G of J0 equal to 1, angle of, what's the angle?
0, 0, 0.
So let me sketch it here. So this is going to be, let's say, I assume this is 1. So this is the point. This corresponds to omega equal to 0. Let me take omega equal to 1. So G of J1. What's the magnitude? What will be the
1 over root 2.
angle minus
45 degrees.
45. And where that will be? In which quadrant?
And the fourth one.
Fourth quadrant, somewhere in here. This is correspond to omega equal to 1. Let me go to extreme. G of J infinity. What will be the magnitude?
Will be 0.
0. Angle
Minus pi over 2.
minus 90. So basically, what we are saying, I have, this is my graph. It will go to 0 along this line. This corresponds to omega equal to infinity. If I want the negative frequencies, this will be the negative frequencies. Okay? This is basically what we are trying to do. This is what we are trying to plot, to make the polar plot. I'm changing omega from 0 to infinity. I'll get this part, and then since it's symmetrical, that will give me the negative part.
طيب يا
So-
دكتور الحين ايش الاكس اكسس وايش الواي اكسس؟
كيف؟
الاكس اكسس هنا والواي اكسس ايش يا دكتور؟ الماجنتيود صح؟
No, this is going to be, no, this is the, let's say, okay, you have E of S equal real plus imaginary, J imaginary. So this represents the real axis, and this is the imaginary. Or if you take, this is the, your reference is going to be, the angle will be 0. This is 90, 180, 270.
لا قصدي الحين في البولر دائما يكون الاكسس اللي هو الهوريزونتال is the يعني kind of representing the magnitude or the
No,
or
no,
we cannot say this, yeah, we cannot say this.
No. We can measure
Yeah.
it exactly if you have, okay.
Yeah, the magnitude is the vector from the origin to
This is equal to 1.
Yeah.
At this
Yes.
point, this is equal to 1. Where do you position 1? It's you know exactly where you position. Look.
Right.
You could, for some of you, if you are not comfortable with the polar, we can do it a little bit differently. Okay, G of J omega equal to 1 over J omega plus 1, which is equal to 1 over 1 plus J omega. Let me write it in the Cartesian, so I have to multiply by the complex conjugate. So this is going to be 1 minus J omega, 1 minus J omega, which is equal to, what do I have in the denominator? In the denominator,
1 plus
omega squared,
Yes.
and I'm going to have 1 minus J omega, which is 1 over 1 plus omega squared minus J omega over 1 plus omega squared. Now do the same. Omega G of 0 equal to what?
Yes, you substitute, so it will be basically 1.
1, which is the real axis. So again, this is what you have the complex. This is the 1. Okay. Suppose now G of J1. What do I have? Where is it going to be located?
So it's going to be, yeah, you just substitute actually.
Which is somewhere in the fourth quadrant. What will be this value? 0 minus also 0. But it is, I mean, it is moving from this direction, which is again the same thing. So either way, I mean, this is a complex, okay. This is we call it G of S plane, which is a complex plane. It has a real part, it has an imaginary. This is the real axis, this is the imaginary axis, and then sketch.
دكتور
ايوه.
الجزء اللي حيكون سيمتريكال الدايركشن حقه كيف بيكون؟
اوكي الدايركشن كيف يكون حق الشيء؟ الحين احنا at the beginning, okay, this is correspond to omega equal to 1. Sorry, 0. صح ولا لا؟ And
اي صحيح.
this is the correspond to omega equal to 1. And this is finally omega equal to infinity. So this, the arrow represent the increase in the frequency. Okay, the arrow.
طب دكتور لو رحنا للجهة الثانية مثلا اوميجا ايكوال ماينس 1 ولا ما ينفع؟
Okay, you take الميرور ايمج حقه يكون complementary.
حيكون في نفس الاتجاه يعني.
بالضبط.
اوكي تمام واضح.
Okay, Shabab, so either you use the Cartesian or the, polar. I prefer the polar because when the systems are complex, okay, getting the real part and imaginary part from the Cartesian by the rationalization will be complicated. Okay, Nyquist criteria. To investigate the stability of the control system, what we need the characteristic equation. And what do we need? We need, okay, the 0 of this one, okay, must be where in order for the system to be stable?
In the left half plane.
In the left half plane. Look, the zeros of the characteristic equation represent the pole of the closed loop system. That's why. So basically, let me let me come back to the feedback system. This is G.
دكتور بس معليش ليش يساوي ما في 1 بعد اللي يساوي؟
كيف؟
بعد اللي يساوي ليش ما في 1؟ يعني it is just K.
بعد اللي يساوي هنا okay, wait a minute. I will come to it. Just 1 second. H. Okay, suppose G and H are given, let's take a specific example. Suppose I will have G of S equal to 1 over S plus 1. And H of S equal to 1 over, equal S plus 2, S and S plus 3. Okay? So what is transfer function? Tell me. T of S. What does it equal to? What will be the transfer function?
Transfer function
Yes.
is G over 1 plus GH.
So 1 over S plus 1 over 1 plus 1 over S plus 1 times S plus 2, S and S plus 3. Okay. This is transfer function. What will be the characteristic equation? What's f of S?
The one in the denominator.
1 plus 1 over, let me rewrite it, S plus 3, S plus 2, 1 over S plus 1. This is the characteristic equation, which is equal to 0. In here, this is the one which you said, Abdurrahman. This is equal to, okay, let me later on put the 0. This is equal to what? S plus 1, S plus 3, and in here I will have S plus, S times S plus 3 times S plus 1 plus S plus 2. This is the characteristic equation, isn't it? Which is this one? So
لا يا دكتور في شيء ما ادري اس بلس 2 مظبوط يعني حطيتها كلها في اس.
ايوه
جميل.
يعني
بس ليش هو حطها؟ ولا انه حطها يا دكتور هنا قال اس بلس زي اي اوفر اس بلس بي اي، يعني حطها فقط كبولز وزيروز، فما ادري هل هو he means the zeros of
لا look this is and the format, okay, this is leading us to what we want. يعني what he's trying to say, okay, tell me now, okay, what are the poles of the characteristic equations? What are the poles of the characteristic equation? للإكزامبل اللي أعطيتكم إياه.
الزيروز حق transfer function.
The zeros? No. The poles of the characteristic equation, those are the poles. What are
0 minus 1 minus 3.
Okay, 0 minus 1 and minus
3, yes.
Exactly. How do you relate them to these poles of G of S, H of S?
They are the poles of G of S, H of S.
So they are the pole of the open loop system.
Yes, but now the zeros. What is the
No. Those are the poles of the characteristic equation. The pole of the characteristic equation are the pole of the open loop system.
Yeah, we don't have a problem with the pole, Doctor. We have a problem with the zero.
Exactly, that's what we want. The whole story, how do I figure out the zeros? The zeros, as you can see, become more complicated. So this is where the theory is going to be. The poles are given. What we want to do, we want to find the zero. So we will come to it. Okay? So the remark in here, sorry. So basically, for a system to be stable, all the zeros of f of S, okay, which are in the numerator, must be in the left half side of the SC plane. What's important in here are the zero of the characteristic equation, which are the poles of the closed loop system. We have to distinguish between open loop.
Yeah, Doctor. Yeah, if you can emphasize this. Now the zeros of f of S is the poles of the transfer function.
Exactly.
You see.
Okay. Well, what Nyquist did, okay, because we would like to see in here, we would like to see all the zeros of the characteristic equation in the left half plane. If I have anything in the right half plane, my system becomes unstable. So Nyquist took special contour. Okay, you start from 0, you let omega equal to 0, go all the way to infinity, take a detour at infinity and come back to minus infinity and come to 0 again. Okay.
Repeat it again, Doctor.
What Nyquist want to do, he would like to sketch this one, okay? He would like, as we vary omega on this one, he would like to see where is f of s will go. What's the shape of s in the complex plane? So he is worrying about the entire area because for stability, all the zeros of f of s must be in here, isn't it? The zeros for stability, I should not have any pole, any zero of the characteristic equation in this side. So he decided to map the entire, you go from 0. I want to represent the right half plane. How do I represent it? I will go from 0 to infinity and go all the infinity, come back in here. Rather than putting it in this shape, what they did, he assumed, look, this is R at infinity. It means that, he's taking the entire right half plane. So what we are going to do, we are going to take a contour. We say the contour is a closed path.
We integrate then, Doctor, or
If?
we integrate over this contour? Or
No, we
what
don't
do?
integrate. We don't do anything. We just count. We
Because
map and then we count. Don't worry about integration.
No, but I want integration. This is what makes things more interesting.
Look, as I said, you have g of j omega, h of j omega. For each omega gets a point. Put it in the plane, in the complex plane. Then go next, until you reach infinity. And that's what, if you remember in the example I gave you, 0, 1, infinity. You go all the way to infinity, which means that you are covering the entire right half plane and come back through the negative, which means negative frequencies from minus infinity to 0.
Yes. Yes.
For each point, get the graph of this one.
For each point in the contour?
For each point in the contour, you get a point in here. Because 1, 2.
Yes. I see now, I see. Doctor, this contour is is famous because I remember I read the paper about this contour particularly is heavily used in finding the inverse Laplace transform.
Okay.
I don't know if you
In this
remember
application,
this.
look, in this application, this is what they have. But again, there is one more thing. If you remember, we said Nyquist, okay, his criterion is based on analytic function. And suppose I have a pole in here, and a pole in here, and a pole in here. Okay. According to the theorem, I cannot pass through the pole. So what he did, he modified the path when you reach the pole. You either exclude the pole or include it. Go in the other direction, you will include it. But don't go through it. They call it the modified, okay, or the generalized Nyquist path. You don't go through a pole, because if you go through it, it will be non-singular. It's going to be singular and you cannot plot it. Okay. Now, let's move. Some concept related to the poles and zeros. This is similar to what I have said before. If f of s is the characteristic equation, first of all, how do I define pole? What's pole? What does pole mean? A pole of transfer function.
Function goes to infinity.
F 0, the function goes to 0. let's come back in here to the feedback system. We said this is transfer function, the direct over the 1 plus loop gain. And this is the characteristic equation.
Right.
Okay. Now, let me stress again, because this is very important issue. If the characteristic equation f of s equal 1 plus g of s h of s, the zeros of the characteristic equation, what do they represent for a transfer function?
The poles of the transfer function,
The pole of the transfer function.
because it's the zeros of the denominator.
Exactly. Okay.
But Doctor, I have an issue with the format that you have shown before, which
Please.
is going from 1 plus g k g s h s to just k, and you decompose the zeros over the decomposition of the poles of the f of s.
Why?
I don't know where is the one, because one will have an effect on the zeros of f of s.
Okay, let me explain this issue. Let's be specific again for the same example. Let's use, okay, g of s we said equal to 1 over s plus, what did you say, 2? Or do we have a 0 in here? I don't know. Let's say this one.
Let's say 2, yeah, no problem.
Equal to 1 over s, s plus 1, and s plus 3 times s plus 3. Okay? So the characteristic equation, f of s,
It's just equated to 0.
1 plus the multiplication of the 2.
Yes.
So it's going to be, okay, 1 over s plus 2 times s, let me put it here, s plus 1, s plus 3. Wait a minute, I did not put any 0. Let me put 0. Let me put some 0. Let's say this is s plus 4. So we'll have s plus 4. Do you have any problem here?
No, now after simplification, we
What is
simplify
equal
what?
to? Put it in common denominator.
Yes, no problem. We will have s plus 4 plus whatever we have in the denominator. Now the issue
Plus
is,
s plus 4.
yeah, exactly.
Those
The issue
are the zeros.
yes, yes.
Is going back to, okay, this is k factorized, and this is factor them.
Yeah, this k, Doctor, is a function of s or not, because
No,
this
constant.
it's just constant. Yeah. So the issue here is that we are decomposing the numerator as a multiplication of s plus zi. But if we go back, we will notice that we have a decomposition of
Abdurrahman, you are complicating life. All what we are saying,
This is what I see, Doctor.
okay, in general, just 1 second. Where are we now? No. What we are
Here.
okay,
Yes.
what we are saying in here, usually so far in the Nyquist and root locus and body, we are giving poles and zeros of the open loop system.
Yes.
Okay.
هنا دكتور الحين البسط يا دكتور في جزء مضروب بلس اس بلس 4. I have the problem with plus s plus 4 لانه هناك حاط الفورمات كلها multiplication.
طيب يا عبد الرحمن, open this up as s plus 2, s plus 1, s plus 3 plus s plus 4. Open it up, collect the term, you get polynomial, factorize the polynomial.
هذه هي بس لأن
ايش المشكلة؟
I thought انه يعني it has to be يعني 1 plus so keep the same format يعني بس خلاص الحين واضح تمام.
هي الكومبليكيشن كلها بالزيرو, that where
الزيرو in the open loop صح, هذه المشكلة.
Okay, so now what we are going to have, we said the zero of the characteristic equation are the poles of the closed loop system. How about the poles of the characteristic equation?
It is the zeros of the T of S.
Not the zero, the pole of the open loop system. The poles of the characteristic equation, which is this one. And they are the poles of the open loop system. Is it clear?
Yes.
Okay.
Also, the zeros of the transfer function. Yeah.
No, not the zero of transfer function. Look, I'm just talking about, okay, simple thing. Okay, I have the characteristic equation has a poles and zeros. The poles of this one. Okay, look at what we have here. Look what we have here. What are the pole? What's the equation of the pole in here? I have 0, -2, -1, and -3. Look in here. What do you have? 0, -2, -1, and -3. They are the same. So what we are saying, the poles of the characteristic equation are the pole of the open loop system. And they are very important. What we want to find out, what will be the zeros? How many zeros of the characteristic equation in the right half plane? Okay. Let's come to the Nyquist criterion. I don't know, is it clear?
Yeah, now it's very clear. بس
Okay.
تعبنا Nyquist.
Right. The Nyquist criterion said we plot f of sigma for each value of omega in the f of s plane and determine the number of encirclement of the origin. Then the number of zeros, which we don't want to calculate, will be in the f of s contour is equal to n naught plus p naught. Now, p naught are the number of poles of the open loop system, which we already know. This will be obtained from the polar plots. So the only unknown, how many zeros? Add those two together and should give you n. It should give you number of zeros. If the number equal to 0, the system is stable. If the number is different from 0, the system is unstable. Let's go back to this example. From here, immediately, if I had the Nyquist, okay, Nyquist contour, which is this one. I have a pole here. I have a pole at -1, -3, and there is a 0 somewhere in here. So how many poles within the contour in here?
No pole.
No poles. So P naught immediately I can find is equal to 0. Now, what I could do for each if I go through the contour by changing omega, for each point I get the sketch. Get the graph. How many times you are encircling? This is f of s plane. Okay. How many times you are encircling the 0? You can get n. Then you apply the formula. This is basically what we are saying.
طيب سؤال دكتور عشان بس نفهم زيادة الموضوع. الحين just a question to understand more. If I know the poles of the f of s, right?
If you know the pole of
f of s, because
the pole of f of s, they are the pole of the open loop system.
Yes. So to find the z0, I have to know two information: the number of encirclements and also the poles of the f of s,
Exactly.
which is actually the zeros of the open loop gain.
The pole of the open loop, the pole of the open loop, not the 0 of the open loop.
the ball, I'm sorry, the ball of the open loop. Now the question is, in practical use, if I know all of this information, yani, if I want to test or testify or know the stability of the system, do I have the luxuries to these all of information to know the poles of the f of s, to know the number of encirclements, or in the real case we don't know all of this information?
No, look, you are given a problem, given the system G, H, this is the closed loop system, this is Y, this is R. You are given G and H. This is given to you. From those, you determine P, because they are the pole of the characteristic equation, they are the pole of the open loop system. So this is given to you. Okay, what you will do, sketch G of J omega as omega goes from 0 to infinity and get a graph. The graph will tell you how many times you are encircling the origin, and that will be n. So you have P, you have n, determine Z. That's all. That's it, yeah.
So,
Okay.
yes.
Now let's take it. Okay, let me. I don't think we'll have enough time for example. But anyway, okay. Suppose, okay. Now, what we have done in here, we are sketching 1 plus G of 1 plus G J omega H of J omega, and we're counting the encirclement of the origin. Now let me take the 1 to the other side. So I will have, this is easier to sketch, and now the criterion is going to be modified, okay, such that, okay, the criterion is going to be modified, okay, P naught will not change. N will be the encirclement of the origin now, sorry, of the -1, not the origin now. Okay, so basically, rather than counting the encirclement of the origin, I will you know, count the encirclement of the -1. This is the -1. Wait. Abdurrahman, please.
From the very beginning, right, Doctor?
الحين انت ما سمعني السؤال حقك لانه كان الصوت فيه ايكو كثير.
تسمعني الحين يا دكتور؟
تفضل.
Yes, I mean we do this -1 because we have already subtracted 1 from
That's correct.
FS, right?
That's correct.
When we
That's
examine LFS. So now we negate kind of the action.
يعني الافورت حقنا اسهل مع this one will be much easier. Okay, so the criteria now, the criteria is P naught is given, as I said, from the open loop system. Okay, then a graph as omega change according to the Nyquist contour, and that will give you, then you will conclude from the addition of those two, Z naught. If Z naught equal to 0, the system is stable, otherwise the system is unstable. Okay, so let's, okay, I think, you know, I don't want to go to the example because, well, it's
Doctor, we need an example.
we will, inshallah, next week definitely we'll have more than one example. Okay, Shabab, I think we'll stop here. If you have it, you can
Sir,
if you want to leave, that will be fine.
Kind of excitement for the coming class, yani, to be continued to the exam.
Okay. That will be fine.
Doctor, I have a
Yes.
question.
Yes.
You said that the poles of the characteristic function are the poles of the open loop system. You mean the poles of the G and the poles of H?
لا دقيقة. Let's say that again. Let me clear this one. First of all, بالله دقيقة, give me 1 minute. Let me stop the recording, and then I will be more than happy to